Hello, everybody. This is for the course MATH2099, Linear Algebra at University of New South Wales. And in this video, we will work on eigenvalues and eigenvectors. And so we will solve some questions related with eigenvalues and eigenvectors. Okay, first, what is the eigenvalue and eigenvector? If we have a linear transformation from a vector space V to another vector space W, and this is the equation. There are some vectors and there are some eigenvalues. There are some real numbers satisfying such equations. And the lambda in this equation is called the eigenvalue. And there are certain types of eigenvectors corresponding to this eigenvalue. So this is a definition. Usually, we call the basis of the let's leave it in that moment. I will talk later then. This is just a definition. So linear transformation, we are applying a particular vector, particular type of vector or vectors, and you're getting some multiple of that vector. Right? These are specific vectors, specific type of vectors, and specific values for each linear transformation. Okay, if A is a matrix form of the linear transformation T, we can replace these equations with the linear matrix form of this linear transformation. Because of the matrices, this lambda times V is equivalent to the multiplications of lambda times identity matrix of V. And then we are taking this on the other side, we would have A minus lambda I times the vector is equal to 0 vector, right? So this is a matrix, and that will be a 3 by 3 matrix. And then you're multiplying the, maybe not 3 by 3, but n by n or something like that is a square matrix. And then you're multiplying a vector in Rn, then you will have a vector in Rn. So this is the 0 vector in Rn. And if this equation has a solution, if and only if the determinant is equal to, the determinant of this matrix is equal to 0. This is because this equation system is a homogeneous equation system. And from the matrix theory, from the other theories, other theorems, we know this theorem. The theorem T says that if you have an homogeneous equation system, the coefficient matrix, determinant of the coefficient matrix is equal to 0, if and only if it has a non-solution, non-trivial solution. This is a very simple reason for it, because if the determinant is not equal to 0, then there exists an inverse of this matrix. And then you multiply this with an inverse of this matrix, multiplying the 0 with an inverse of any matrix will be the 0 matrix again. So the right-hand side will be all 0, but left-hand side will be the vector. And immediately you will realize that that vector has to be the 0 vector. So that's a trivial solution. So if the determinant is not equal to 0, it will be a trivial solution. So this is pretty clear to see or easy to see. Okay, so we realize that the equation has non-trivial solution if and only if the determinant is equal to 0. Now, in this is an equation, right? And lambda is not known because we first would like to find out what is the eigenvalues. We would like to figure out eigenvalues and eigenvectors. First, we find eigenvalues, then we find eigenvectors corresponding to eigenvalues. Okay, this idea represented here gives us how to calculate the eigenvalues. And the determinant of this matrix A minus lambda I is called the characteristic polynomial. And the roots of these polynomials are called the eigenvalues because the roots, the unknown here is the lambda, and the roots of this polynomial gives you the eigenvalue. If you have a 3 by 3 matrix, you have at most three roots of this equation. If we assume that we found all the eigenvalues, n eigenvalues for the n by n matrix A, then for each eigenvalue, we would like to calculate the eigenspace. Eigenspace are the vectors that satisfying this equation for each lambda. What is this? This is basically the kernel space, right? The vectors satisfying this equation, basically there is the kernel space of this transformation. This is what we are saying here. So lambda I eigenvalue, lambda I eigenspace, the vectors corresponding to the eigenvalue lambda I is the kernel of that of this equation, kernel of that linear transformation, which is that one. This is exactly what it says. So lambda I, since we figured out what are the roots of this polynomial, lambda i's here are known real numbers or complex numbers. So the eigenvalues are here are the numbers, and then when we put it here, we have a matrix and we calculate the kernel of this matrix. It will give us an eigenspace. This is the eigenspace corresponding to eigenvalue lambda I. So that's the definition of it. Any vector in this space, we call it the eigenvector corresponding to eigenvalue lambda I, or simply we say it eigenvector. But in general, when we are doing the calculations, and you will see, when we are talking about the eigenvector, we usually refer to the basis of this space. Because there are infinitely many eigenvectors, lambda eigenvectors, or eigenvectors corresponding to eigenvalue lambda I is infinitely many. And when we are talking about the lambda I eigenvector, we refer to the basis of this vector space. So this is definition, and why it is important. There are many reasons for it, but one of the reasons is that diagonalizability of a matrix. So if you have a matrix A, which is n by n matrix, we call it, this is a definition, diagonalizable, if there exists a diagonal matrix T, an invertible matrix M, such that A is equal to M d M inverse. If lambdas here are the eigenvalues, and the M vector, M matrix, can be constructed as this matrix, each columns will be the lambda I eigenvectors. But it is very important to keep up with the order. So if you have a lambda 1 in this 1, 1 position for this diagonal matrix, then the first column should be an lambda 1 eigenvector, or a basis of the lambda 1 eigenspace. If this is lambda 2, this should be lambda 2 eigenvector. So all correspondence, it shouldn't be mixing out. So this is a definition of the diagonalizable matrix. And not every matrix is diagonalizable. We can find eigenvalues and eigenvectors for every matrices, every n by n matrices. We can find eigenvalues, eigenvectors, but not all of the matrices are diagonalizable. So there exists a rule for it. There exist some conditions for it. And if the matrix is diagonalizable, if and only if the union of the bases of the all eigenspaces needs to give us the number n. This is the condition. It will make sense when we are doing the exercise. But A is diagonalizable matrix if and only if the union of all basis elements of the eigenspaces of the matrix A gives you the n, which is the size of your matrix, then it is diagonalizable. And this is an if and only if case. And we will sort of do it in a step-by-step way. So algebraic multiplicity, as another way of doing this criteria, is to looking at algebraic multiplicity and the geometric multiplicity of the eigenvalue. So eigenvalue, algebraic multiplicity of an eigenvalue, we will denote A m lambda I. That is the multiplicity of the root lambda I in the characteristic polynomial. Right. Because, yeah. And the geometric multiplicity of the eigenvalue will be the dimension of the eigenspace. So if the matrix is diagonalizable if and only if the algebraic multiplicity is equal to the geometric multiplicity for each eigenvalue of the matrix. This is also equivalent to this condition, because if you have, for example, think much more simply in that moment. Think you have a 3x3 matrices, and you have three distinct eigenvalues, and each eigenvalue corresponds an eigenspace generated by one vector. That means that the algebraic multiplicities and geometric multiplicities are the same, because each of them 1, 1, 1. And when you add them up, you have 3, which will give you the size of the diagonalizable matrix. So there will be no degenerate form in the structure, and you can find a basis of the whole space by looking at the basis of the eigen spaces of the matrix. So that's the idea. That's another way to put it that way. So if you can find by looking at all eigenvectors, all the bases of the eigen spaces of the matrix gives you the basis of the whole space, then you've done. The criteria for this is much more simpler to check, right? This is algebraic multiplicity is equal to the geometric multiplicity for each eigenvalue, then A is diagonalizable. Okay. Now, why we want diagonalization? Diagonalizable matrices are used for the big computations and like a powers of something. It is easier to calculate a power of the matrix if we know how to decompose, how to diagonalize it. In that case, for example, if A is diagonalizable matrix, if we look at the power of this matrix, you need to multiply this matrix p times all the time by itself. If it's a large matrix and it has lots of number in it, it will be very hard to do it. But if we separate it, if we use diagonalization of the matrix A, then this is what happens. Then we have m d m inverse p. This is the power of it. Well, the multiplications of this m d m inverse p times. But each time, these middle terms will give you the identity, because this is m inverse m, m inverse m, m inverse m. All of them will be just an identity. And then you will have only one m in the beginning and m inverse in the end. In the middle, you will have d to the p. And the diagonal matrix, taking the p-th power of a diagonal matrix is very easy. It will be just the p-th power of the diagonalization. So this is an important application for the diagonalizable matrices. Of course, there are more because matrices are complex structures, and if we can use some kind of a decomposition, like a diagonalization, will be easier for some purpose of the computation of things. Okay, let's do some examples about the eigenvalues and eigenvectors. Now, to consider, we have bunch of matrices, and we would like to find out eigenvalues, eigenvectors, whether it is diagonalizable, What is the algebraic multiplicity, geometric multiplicity? If it is diagonalizable, what is the end power of this diagonalization of this matrix in terms of the diagonalized form? Okay, assume that we have this matrix, C, 2, minus 1, 1, 0. This is a 2 by 2 matrix. And let's calculate the eigenvalues first, right? That's the first thing. So we would like to find out determinant of C minus lambda I is equal to 0, is the characteristic polynomial. We would like to find the root of that polynomial. So identity matrix, as we know, we have ones on the diagonals and zeros elsewhere. So it affects only the diagonal entries. So that will be 2 minus lambda, 2 minus lambda and minus lambda on the diagonal will be affected, and all the others will be the same. So that's 1 minus 1, 1 minus 1. Determinant of 2 by 2 matrix is the multiplications of the main diagonal minus the multiplications of the opposite diagonal. That is, this times this minus this times this will be the lambda square minus minus 2 lambda and plus 1. So this is lambda minus 1 square. Okay, lambda is equal to 1 will be an eigenvalue and with multiplicity 2. So this multiplicity will give us the algebraic multiplicity for this eigenvalue. Algebraic multiplicity of lambda is equal to 1 is written by AM1 is equal to 2. Now we would like to calculate the eigenspace corresponding to this eigenvalue. So one eigenspace is E1, which is equal to kernel A minus, you're placing this eigenvalue into here, which is minus 1, and then I. That will be kernel 1 minus 1, 1 minus 1. And the kernel, now we would like to find out the kernel of this linear transformation. So I'm going to do the row operation just here. So adding this row to here will give me this row, this element, and this element 0. This is what I'm doing here. So the kernel of this will be just x plus y is equal to 0. Basically, x is equal to minus y, and y is a free variable. So the minus 1 and 1, which is one vector, will be the basis of this kernel space. So this means that the dimension of E1 is 1. It means the geometric multiplicity, geometric GM, 1, which is the dimension of E1, is 1. Algebraic multiplicity is 2, this is what we found, and geometric multiplicity is 1, that's what we found here, and they are different, they are not the same. Because of our criteria, it says that it has to be the same in order to be able to make this diagonalizable. This matrix is not diagonalizable at all because algebraic multiplicity is different from the geometric multiplicity. Okay, now let's do this another example. And this is the matrix T, but I will change the name A because of the consistency of my notations. We would like to find out first eigenvalues. So we would like to find out the determinant of the A minus lambda I. So this matrix, we are taking away minus lambda onto the main diagonal entries. So this is 2 minus lambda, 1 minus lambda, 1 minus lambda. And we would like to calculate the determinant of this. So we could, whatever you wish to calculate this determinant, you can do it. You can make some entries 0 and open up with that way. It is possible to use this row or this column to open it up, or you can do it with the symmetric method, because this is just a 3 by 3 matrix, multiplication of this 3, this times, this times, this time, this time, this time, this time, is give you the symmetries with respect to the main main values. So this is 0, this is 0, nothing left, only we have 2 minus lambda, 1 minus lambda square. And then for the opposite diagonal entry is minus 1 minus lambda for this. And this one will give you 0. This one will be minus 1 minus lambda, which is that one. Here we have just organizing these values to this polynomial. We will find that lambda 1 minus lambda, lambda minus 3 will be the solutions for the determinant of a minus lambda I. And the roots of this polynomial will be lambda 1 is equal to 0, lambda 2 is equal to 1, lambda 3 is equal to 3. So the eigenvalues of A, it will be 0, 1, 3. Okay, we found the eigenvalues. Now our duty is to find out the eigenspaces and the dimension of the eigenspaces and eigenvectors, the basis of the eigenspaces. Algebraic multiplicities, let's point out the algebraic multiplicities in that moment. We have 3 roots, and each of these roots appears once, so algebraic multiplicities of each of them is 1. Okay, now let's do the zero eigenspace. Zero eigenspace denoted by E0, which is the kernel of A minus 0I. Then it makes it just a kernel of I. So, sorry, A. And then we do apply some row operations. In some way, then you will obtain this reduced row echelon form. The last row says that the Z component, the third component, will be free, and the first and second will be giving you x is equal to minus z, y is equal to plus z, and z is equal to lambda will give you this. And so the basis for this eigenspace will be minus 1, 1, 1, minus 1, 1, 1 will give you the span of this vector. This is the basis of the E0, 0 ions, E0, 0 eigenspace. So we found a one basis vector, which means that geometric multiplicity of the eigenvalue 0 is just 1. Okay, so this means that they are equivalent, right? This first condition satisfied. Algebraic multiplicity of 0 is 1. Geometric multiplicity of 0 is 1. This is what we wished, right? That happened. So what we have the others to check that we haven't finished yet. So we need to calculate each eigenspace for each eigenvalue. So one eigenspace will be E1, that is the kernel A minus I. If you take the ones on the matrix A on the diagonal, I think you need to see that video. Okay, just take the ones over this matrix, then you will have 1 here, 0 here, 0 here. This is what happened. So this will be 0 and this will be 0. Yeah, when you take the row operations, then you will get, when you're doing this operation, you will have, you can get rid of this one, and then you get this one, and then you will have 1, 0, 0, 0, 0, 1. The last row is Z corresponding, so it's a free variable. And the first row, x is equal to 0, gives you x is equal to 0. Second row gives y plus z is equal to 0, which is y is equal to minus z. So the vector corresponding this one will be just if you say z is equal to lambda, will be 0 minus lambda lambda. So that will, the vector that spans of this space will be 0, 1, minus 1. The basis of the kernel will be the 0, 1, minus 1. And this is the one eigenspace. Geometric multiplicity of the eigenvalue 1 is the dimension of the eigenspace with respect to the eigenvalue 1 is 1 because you have one vector which spanning which is the basis of the E1. Now we have the last one, E3. We need to check 3i space, we need to calculate a minus 3i. So this time you are subtracting 3 above on the diagonal. We need to calculate the kernel space of this, find the basis of this kernel space. Applying the row operations, you will get this matrix in the end. Again, the last row says that z is a free variable, and the first row says x minus x is equal to 2z, and y is equal to z, and z is a free variable. If you say z is equal to lambda, you will get 2, 1, 1 is the basis of this kernel space. So we have one basis vector for this ion space, geometric multiplicity of the eigenvalue 3, which is the dimension of E3 is 1. Okay, what is the picture in that moment? So we have the lambdas, eigenvalues here, and algebraic multiplicities are 1, and geometric multiplicities are 1. And these are all saying to us that A is diagonalizable. And on the other hand, we found vectors, basis vectors of this each ion spaces. And these vectors, by just putting them together, will be a form of a basis on R3. So we will be able to get everything in that space, right? If it's a 3 by 3 in R3, but n by n, you need to get n matrices, vectors to form a basis for the n-dimensional space if it's an n by n matrix. It means that A is diagonalizable, and the theory tells us that how we find this diagonalizable form. M will be this is the zero ion space. This is a zero ion space, zero ion vector, which is the basis of a zero ion space. One ion vector and the 3 ion vector. And this is 0, 1, lambda is equal to 0, lambda, these are the ion values, right? And the ion value 0, this is the ion vector 0, 0 ion vector. Ion value 1, this is the 1 ion vector. Ion value 3, this is the 3 ion vector. This is a 3 ion vector, means is the basis of the ion space corresponding to the ion value 3. Okay, so we have M, MD, so we want to write it down. A is equal to MD, M inverse, right? This is what you want. So we have an M inverse here. We need to calculate the M inverse. As you remember how we calculate M inverse in 3 by 3 matrices here. We put the M's here, an identity matrix here. And then you apply the row operations until you get the identity matrix in this corner. And whatever you got here will be the M inverse. I'm not going to do the whole calculation, but if you do that, you will find the M inverse is this matrix. You can check by just multiplying M times M inverse in a corner. You see that M inverse will give you the identity matrix. So this is really the inverse of the M. And when we write it down, MD, M inverse, and you can do the checking as well. Write it down, these matrices, and multiply together, and you will find the matrix A, which means that you've done the correct calculations. This is the checking point. And if you want to calculate the nth power of this diagonalized matrix, we will have M, as we've done in the theory. The nth power will be just the M and D to the N and M inverse. That will make it our life is very easy because the n power of the diagonals will be just 0 to the n, 1 to the n, 3 to the n. And this is M inverse. If we multiply these three matrices together, we will have a matrix of this kind. And this is for each natural number n is satisfied. That is the applications of the application of the diagonalization of the matrix A to the nth power of the matrix. So that's what it is. And this is very useful for some problems to solve. That's all for this this video. It might be a little dense in that video, so you might need to repeat. It takes a bit of time. It's new concepts, how to get it, how to put the things together. I hope it is useful for you. It is helpful for you. Thank you very much for this.